Okay, so this is the last topic that we're doing now. Let's start with this representation of data. So in representation of data, first of all, you need to be able to find different measures of central tendency and measures of dispersion. Central tendency are three types of measures: mean, median, and mode. They give you one value that is supposed to give you the average of the whole data. It should represent the whole data. Okay, these are called measures of central tendency: mean, median, and mode. First of all, how do you calculate them from ungrouped data? Mean is straightforward. For mean, you just add up all the values, sigma x divided by the number of values, and you get the result. That's fairly straightforward. Median, you just sort the data, and the middle value in that sorted data, that's going to be the median. If it's an odd number of values, then it's going to be one value from the data itself. If it's an even number of values, then you would get two values in the middle, and you take their average, and that gives you the result. Now, for ungrouped data, we can use this formula n plus 1 over 2, n plus 1 over 2 to find the position of the median, n plus 1 over 2. For example, if the number of values is 7, you say 7 plus 1 divided by 2, that gives you 4. So the fourth value is going to be the median. In the data, the fourth value is 5. That's the median. Okay. If the number of values is even, for example, if we've got this set of values, n is equal to 10 in this case, 10 plus 1 over 2, you get 5.5 from that. Now, there's not any 5.5th value, right? It's the position has to be an integer. So what we do is, this is 5.5. We say the median is going to be the average of the fifth value and the sixth value, right? And they are 34 and 36. So I find the average, and that turns out to be 35. That's how you find median in this data. Mode is just the most repeated value. So in this case, for instance, you have 5 coming twice, so that's your mode. That's 5 basically in this data. Sometimes you can have multiple modes as well. If you've got multiple values that are coming coming the same number of times, and that's the highest number of times, you can have multiple modes sometimes as well. But central tendency measures are not the only measures that are used to describe a data. For example, in this case, you have two sets of data. Both of them have the same mean, the same median. However, they're actually different from each other because the variation in the data is very different, right? These points are very different as compared to these values. These are not that different. If we just remove that from here, these values are very different from each other. These are all very close to each other, right? So even though the mean and the median for these turn out to be the same, the variation is not the same. So we need another type of measure to be able to describe variation in the data as well. So we have some measures that we call measures of dispersion. The other names for these are measures of variation, measures of spread. There are 4 of them that we need to know about: range, interquartile range, standard deviation, and variance. Range is just maximum value minus the minimum value. But it's not a very good measure in practice because it's affected by extreme values. So if you had, for example, another data point here that was 150, then the range of the upper data, that is going to be 35. Range of the lower data, that's going to become 150 minus 18, and that's 132. And that's affected by this extreme value, even though most of the values are very close to each other. But that one extreme value affects the range. So range is affected by extreme values, but that's one measure that you can sometimes use. But a better measure than range is interquartile range. Now, what are these measures supposed to do? They basically give you how much variation is there in the data, right? So looking at these values, you could say that, okay, data for A is much more varied as compared to data for B. But how do you quantify that? These measures are used to quantify that variation. One is range, another is interquartile range. How is interquartile range found? It's the upper quartile minus the lower quartile. Now, in ungrouped data, there's a specific method that we use to find interquartile range. You need to make sure that you use these formulas. Do not use formulas here. In interquartile range, do not use any direct formulas for finding lower quartile and upper quartile. They will not always work. Sometimes they will work, sometimes they won't. You would not know in the exam if you're getting the correct answer or not. Those formulas, 3n over 4, n over 4, they do not work. How exactly do you find this interquartile range? Let's say you've got this ungroup data like this. These are 11 values in total. First of all, for finding interquartile range, you find the position of the median first of all. Where is the median going to be in this? 11 plus 1/2, that's the sixth value, that's 20. 20 is the median, so this value is the median in the middle. Now, median divides your data into two parts, one on the left side, one on the right side. On the left side, the median of this part, that is going to give you the lower quartile, and the median of the right side in ascending data and data that's sorted in ascending order, the right side, the median of that part is going to give you the upper quartile. Okay, and that's how you find interquartile range. Then interquartile range is upper quartile minus the lower quartile. So for ungrouped data, do not use formulas. They do not always work. Okay, now in this case, the value number of values was odd. What if it was an even number? What happens in that case? For example, you could have a data set like this, n is equal to 12 in this case. You've got 12 values. In this case, if you find the median position is going to be 6.5. That means the average of sixth and seventh value. Now, this is the sixth value, this is the seventh value. Median is going to be between them. Median is going to be in the middle of them. Now, on the left side of the median, you have these 6 values. On the right side, you have these 6 values. You have to consider 20 and 25 on these sides as well. Now, the median of the left side, what's that? That's the average of 5 and 11. That's 8. That's the lower quartile. Median of the right side, that is average of 31 and 40. So the upper quartile is 35.5. Find the difference and you find the interquartile range from that. That's the process. That's the method that we use to find interquartile range for ungrouped data. Do not use formulas here. Then we've got standard deviation. Standard deviation is another measure that's the most widely used measure in practice. We use this to find variation in the data as well. The idea in this case is it gives us the average distance of the values from the mean. That's a rough interpretation of this. That's not the exact interpretation. It's the rough interpretation. It's the average distance of the values from the mean value. Now, how is it calculated? Let's say you've got a set of values of x, 13, 5, 21, and so on. You find the mean first of all. Mean is 15. Now, one way to calculate standard deviation is this, that from each x value, you subtract the mean. Each value, you subtract the mean. So you find x minus x bar, and then you square those values. You square all of those values, add them up together, sum of all of these values. We say that's sigma x minus x bar whole squared. That's going to be your numerator. And in the denominator, you have n, which is 6 values in this case. Take square root of that, and that gives a standard deviation. That's one formula that we got for standard deviation. Sigma x minus x bar whole squared divided by n. Okay, so you subtract from each value the mean. You add up all of those values. That becomes the numerator. And then after squaring, you add them. And then you divide by n, take square root, that's the standard deviation. This is one way to calculate standard deviation. Another way is this. Both of these formulas are given in the formula sheet. This is sigma x squared over n minus x bar whole squared. We will mostly be using the second formula for standard deviation because that's simpler, that's more efficient. This is the one that we will be using. These are equivalent to each other, but mostly the second formula is going to be simpler. So we'll be using that. So the same data, if you wanted to use the second formula, how would you do that? You have sigma x squared here. You evaluate x square values for each of them, add them up together. That gives you sigma x squared. That's going to be your numerator. Divide by the number of values, which is 6 in this case, minus the mean squared. Mean is 15. And that gives you the standard deviation. That's 6.66 as well. Both of these formulas work every time. When you have data given in this form, you should use the second formula. That's much more efficient. The first formula is normally only going to be used for ungrouped data when the question gives you this information. Instead of giving you values, instead of giving you individual values, if they give you this information in the question themselves, then in that case, you would use this first formula. But if you've got raw values like this, then using the second formula is more efficient. Okay. All right, let's move on. So that's standard deviation. The number that you have inside the square root, in this case 44.333, that's called variance. That's another measure that we've got for variation or spread or dispersion. Variance is just the square of the standard deviation. So if standard deviation formulas are these, then if you just remove square root from these formulas, you get variance from that. Variance is given by these two formulas. Variance is square of standard deviation. These are four measures of dispersion that we've got: range, interquartile range, standard deviation, and variance. Now that's for ungrouped data. What about group data? Group data is when you have values in the form of a frequency table, right? Frequency table, that's called group data. Let's say we've got some data like this. We've got information about the number of pets owned by some families, and we've got so we collect some data like this. We've got some families for which we have this information, the number of pets they own. So there are 6 families in the data that own 0 pets, 20 families that own 1 pet, 7 families that own 2 pets, and we want to find, let's say, the mean of this data. How do you do that? We've got this information inside the table. The formula for mean that we have is sigma xf divided by sigma f. There's a logic behind it where this comes from, but we'll not go into that. It's given in the formula sheet. Sigma xf divided by sigma f. All you have to do is, in the table, add another row to the data, x times f. So you just multiply these two numbers, x and the frequency, add them up all together. That gives you sigma xf. Sigma f is the sum of all frequencies. Divide them and you get the mean from that. Okay, sigma xf divided by sigma f. For ungrouped data, the formula was sigma x over n. For group data, in place of sigma x, we've got sigma xf. In place of n, we've got sigma f. The total number of values is now given as sigma f, the sum of all frequencies, right? Similarly, for standard deviation as well, the formulas that we had in ungrouped data, they were these, right? In group data, they convert to this. Again, these formulas are given in the formula sheet as well. So what happens is you have frequency here in the numerator multiplied by this, and in the denominator, n is replaced by sigma f. And in the second case as well, x squared is multiplied by frequency, and in place of n, we've got sigma f. These are the grouped tables formulas for standard deviation. Frequency tables formulas, both of these are given in the formula sheet. In this case as well, it's often more efficient to use the second formula rather than the first one. Okay, so how would you use that? In an example, let's say you've got that same data set as before. The formula that we will be using for standard deviation is this: sigma x squared f divided by sigma f minus x bar whole squared. You add another row to the data. You already need the mean of the data for this, right? So you have to find the mean. For mean, you need x times f. You have that row in the data already. That gives you sigma xf. Add another row to the data that represents x squared times f. That's another row. Once you have these values, sigma xf, sigma x squared f, all you have to do is input them in the formula. Find the mean first of all. The mean turns out to be 1.633. Put that mean here along with sigma x squared f and sigma f, and that gives you the value for standard deviation. That's how you calculate standard deviation for group data. Mode is just the value that has the highest frequency. So if you've got that data, what's the mode value? 10 is the highest frequency, so mode is 1. Okay, mode is not 10. Mode is the value of the variable corresponding to that highest frequency. That's going to be 1 in this case. What about the median? For median and interquartile range, etc., in this case, you can use formulas. In this case, n over 2 works as well for median, n plus 1 over 2 works as well. Both of them will give you the same results. In this case, they will give you tables in a format in which n over 2 and n plus 1 over 2, both of them will give you the same results. So in this case, if you have to find median, how do you do that? You've got sigma f equals to 30. So in place of n, you've got 30 here. The number of values is 30. Divide that by 2, that gives you 15. 15th value is going to be the median. And now we count from the beginning. We've got 6 values until this point, right? So from 1 to 6, we've got these. Then from 7 to 16, the next 10 values up to 16, they are ones. So where does the 15th value lie? 15th value lies in this interval. So the median in this case is also supposed to be 1 for that reason. Okay, what about interquartile range or range? Range is just the maximum value minus the minimum value. Maximum value in this case is 5, minimum value is 0. 5 minus 0, that turns out to be 5. What about interquartile range in this? Let's think about that. In this case, for group data, we can use formulas. They work n/4 and 3n/4, right? The formulas work in this case. Or you could also use n plus 1/4 and 3n plus 1/4. Those formulas are going to work for group data. Okay, there's azan going on here. We'll have a 1-minute break and then we'll see. Okay, so how do you find interquartile range in this case? In this case, you are allowed to use formulas n/4, 3n/4. In ungrouped data, you could not use formulas. Now, n is 30 in this case, so you can say 30/4, that's 7.5. That means the average of 7th and 8th values. Now, in this case, what would happen would be both of these values are going to be in the same interval. They will give you tables in that format. Upper quartile, that's 22.5th value. That's the average of 22nd and 23rd value. Now, let's think about this. Let's think about the table. The first 0 has a frequency of 6. So from 1 to 6, we've got these values. The next 10 values up to 16 are 1s. So 7 to 16, we've got these values. And then plus 7, 16 plus 7, that's 23. 17th value to the 23rd value, we've got this interval and so on, right? Now, the lower quartile is going to be the average of 7th and 8th value. Both of them are in this interval. So that's 1. Average of 22nd and 23rd, both of them are in this interval. And this, both of them are here. So the upper quartile, therefore, is 2. Find their difference, and that will give you the interquartile range. Yes, in this case, n plus 1/4, n/4, they will both give you the same result. They will give you the tables in that format in which both of them are going to give you the same results. Okay. So in group data, you can use these formulas: n/4 for lower quartile, n/2 for median, 3n/4 for the upper quartile. N here is the same thing as the sum of all frequencies, sigma f. Now, then you can have data in the form of intervals as well. The only thing that's different here is when you're calculating the mean and standard deviation, you use the midpoints for these calculations. You use midpoints for calculations of mean and standard deviation. So you would say, if this is the interval 2 to 3.5, the X value in the formula is going to be the midpoint of that interval. What's the midpoint of 2 and 3.5? 2.75. For this interval, we've got 4 and so on. How do you find midpoints? Find the average of these numbers. 2 plus 3.5 divided by 2, that's 2.75. Similarly for the rest of the numbers. The rest of the intervals, you have the midpoint. So now you have these X values. And you have these frequencies. This is what you will be using for your calculations, X values and frequencies. Evaluate X times F, evaluate X squared times F, and input values in the formulas, and you'll get the result. Now, this is very important. Sometimes they will ask you in the questions, why are these values of mean and standard deviation? They are estimates. Why are these estimates? These are not exact values. These are estimates because we are using midpoints for our calculations. We're using midpoints for our calculations. Now, the actual values in the data could be anything. For example, if there are 8 values between 2 and 3.5, it is possible that all of them were maybe 2.05, 2.1. All of them were small numbers. It's possible that all of them were large numbers. We are just using 2.75, which is the average of this interval. It's not necessary that the actual average of the values that you have is 2.75. Since we don't have any other information, any more information, the best we can do is we can just use the midpoint. So we would say these values are estimates because we do not know the actual values. We do not know the actual values. We're just using midpoints in our formulas. So the values of mean and standard deviation. So the values of mean and standard deviation that we would get from this calculation, they're going to be estimates. Okay, so we'll say that we do not know the actual values, we're just using midpoints. So that's why these are estimates. Now, in case of intervals as well, they can ask you to find the modal class. How do you do that? Just the class or interval that has the highest frequency. In this case, that's 5.5 to 7. That's your mode. Interval in which the median lies, exactly the same process, n over 2. That gives you 52nd value, and then figure out where the second value lies. 34th to 61st values, they are in this interval. So this is the interval in which you've got the median, 4.5 to 5.5. Okay, that's pretty basic stuff. Then in case of range and interquartile range, when you have intervals given, they often ask you for the greatest possible value of range and the least possible value of range. So they will not ask you to find range directly in a question that involves intervals like this. They will ask you to find the maximum possible range or the minimum possible range. Now, how is range defined? Range is defined as the maximum value minus the minimum value. If you want to maximize this, remember the concept of upper bound, lower bound in O levels as well. If you want to maximize this, you would want the positive value to be as big as possible, minimum value to be as small as possible, so that the difference becomes maximum. So greatest possible range, that's the maximum value minus the minimum value. Now, maximum value is going to be in this interval, minimum value is going to be in this interval. If we want the greatest possible value of the range, what we would do would be, we would use 9 from here and 2 from here, right? The extreme values on both sides, and that's 9 and 2. That's going to give you 7. Okay. Now, similarly, for the least possible range, the maximum value should be as small as possible. The minimum value should be as large as possible. Now, we know there are some values in this last interval. There have to be some values here. There are 12 values there. And there are some values in the smallest interval. The least possible range would be if all the values in the first interval, they were 3.5. And all the values in the last interval, they were 7. So we would want the maximum value to be as small as possible, minimum value to be as big as possible. So what are those values going to be in this case? We say they are 7 from here and 3.5 from here. These are the values that are going to give us the least possible value of the range. That's 7 minus 3.5, and that gives you the result. That's 3.5. Okay, so that's how you find the maximum possible range and the minimum possible range. Class width, there's no point of finding class width here. Class width is only needed for histograms. We'll see that later. In this case, there's no logic of using class widths. Okay, let's move on. Interquartile range as well. For interquartile range as well, they will ask you to find the maximum possible value of interquartile range and the minimum possible value of interquartile range. Okay, how do you do that? You first of all find in which interval the lower quartile is and in which interval the upper quartile is. You can use n/4 and 3n/4. n/4 is 26. 3n/4 is 78. 26th value lies in this interval. 78th value lies in this interval. Okay, so these are the two intervals that we've got. These are the intervals in which you've got these values. Now, this is one interval, this is the other interval. Upper quartile is going to be in this interval, lower quartile in this interval. What's the maximum possible interquartile range? Interquartile range is defined as upper quartile minus the lower quartile. For greatest possible interquartile range, we would want the upper quartile to be as big as possible, so that's 7. Lower quartile to be as small as possible, that's 3.5, and that will give us 3.5. For least possible interquartile range, we would want the upper quartile to be as small as possible and the lower quartile to be as big as possible. Then the difference will become minimized. So that's 5.5 minus 4.5, and that gives you the result that is 1, and that's the least possible value of the interquartile range. Okay, so in case of intervals, they can ask you for greatest and least possible values of range and interquartile range like this. Now, the interval data could be in other forms as well. In this case, we had dashes between them, and there were no gaps between the intervals. They can give you intervals in this form as well when you have inequalities. So from 0 to 5, 5 to 10, and so on. Again, the idea remains the same in this case as well. Since there are no gaps between values, we would just find the midpoints, and these are the frequencies. Add another row to the data, xf and x²f, and use them to find the mean and standard deviation. So that remains the same. However, if you get some data that looks like this now, in which there are gaps between intervals, So from 1 to 25, 26 to 35, 36 to 45, now there are gaps between intervals. These are gaps, right? So in this case, you should first ideally adjust the intervals. Now, in this case, it would not make a difference, and because the midpoints, if you were to find them directly from this or from true class boundaries, they will turn out to be the same. But I'll show you another example in which it does make a difference. So what you generally do is find the true class boundaries, like you do for histograms. You want to eliminate the gap between values. How would you do that? You can say 25 is where the first interval is ending, 26 is where the next interval is starting. The actual boundary is going to be at the midpoint of these two values, and that's 25.5. Okay. Similarly, here it's 35.5, 45.5, 55.5, and using the same pattern, you can adjust on the sides as well. This is 90.5, this is 0.5. These are the actual class boundaries. We call these true boundaries of this variable, because it's time. Time can be in decimals as well, right? So what if it was 25.3? How do you know which interval to put that in? It rounds off to 25. It's less than 25.5, right? So we put that in the first interval. So that's why we need these true class boundaries. They're going to look like this. And then using these boundaries, what you can do is you can find the midpoints, find the values of x like this. You have frequencies, find xf, find x²f, and then do these calculations like you would normally do. Now, in this case, as I said, finding midpoints from the actual data or from this data, that's not going to make any difference in this particular example. But what if you had something like this? It's slightly different from that, in that I've changed the first value here such that it becomes 0 to 25. So the first interval starts from 0 to 20. It goes from 0 to 25. Now, when you adjust the intervals for this, what happens is this is 25.5, 35.5, 45.5, 55.5. You adjust the sides on the same pattern as well. So you adjust the right-hand side. On the right side, you have 90.5 here. But on the left side, you had 0 here already. You had 0 here in the original data. Now the variable is time. Time cannot be negative. So we cannot say that the first interval starts from minus 0.5. That would not make sense because time cannot be negative. So the first interval in this case will have to start from 0. Now, that means the midpoint of these two values is going to be 12.75. If you were to find that midpoint from the original value, 0 and 25, that will turn out to be 12.5, and that would be wrong. So in this case, if you had to find the mean and standard deviation, their values will turn out to be wrong if you find the midpoints from this, because the midpoint of the first interval is going to be 12.75 from the true class boundary. So you should first adjust this and then do this. Normally, this problem is only going to be when you have this extreme value on the other side, that is 0. Otherwise, you can do it directly as well. But when you have an interval that starts from 0 and you cannot adjust on that side, but on the other side you are adjusting, that means there's going to be a problem, and you have to use true class boundaries. In that case, adjust these intervals first of all, and then find the midpoints after that. Okay. Now, sometimes what happens is they give you cumulative frequency table. In the questions, rather than giving you a normal table, they give you a cumulative frequency table. So they give you this table. Okay. And using that, you have to find the mean of the distribution, the standard deviation of the distribution. How do you do that? You would convert it to a normal table, first of all. Normal table that has two-sided intervals. How do you do that? Less than 40, you can say, let's make intervals like this, 0 to 40. And then the next one is going to be from 40 to 50, 50 to 60, and so on, using these values as the upper boundaries, upper limit for each interval. These are the intervals that you end up getting from this, right? 0 to 90 like this. Now, find the corresponding frequencies. 0 to 40, you've got 0. Less than 50 had 12 values in total. There was 0 value less than 40, so that means all of these values are going to be between 40 and 50. So this frequency is 12. And then similarly for the next values, if less than 60, you've got 34 values in total. Less than 50 were 12 values. How many do you have from 50 to 60? That's only 22. You basically find the difference 34 minus 12. So it's the opposite of cumulative frequency curve. We are doing the opposite. So we'll subtract these values like this. 34 minus 12, that gives us 22. 64 minus 34, that gives us 30. 92 minus 64, that's 28. 144 minus 92, that gives you 52. And this way you find your standard table. And now you've got these intervals, you find the midpoints. The midpoints turn out to be 20, 45, 55, and so on respectively. So now you've got these X values, you've got these frequency values. These are the ones that you will now be using to find the mean and standard deviation. The rest of the process remains the same. You find XF, you find X square F, input them in the formulas, and you get the result from that. Okay, so this is possible as well, that they give you a cumulative frequency table, and you have to find the normal table from that, and then do those calculations. Another concept that you have here is linear transformation. It's also called coded data sometimes, or linear transformation. Now, what's this? This is the next concept that we have now. Let's consider two variables. Let's say there's one variable that is X, and there's another variable that is Y. And they are related like this, that Y is equal to X plus 7. Y is equal to X plus 7, right? For every value of X, if you add 7 to that, you get the corresponding value for Y from that. Now, when you have two variables that are related like this, linearly, if you were to find the mean for one, mean for the other, you would notice that the relation between their means is also going to be the same. So if Y is equal to X plus 7, then Y bar is going to be equal to X bar plus 7. Okay. And what about standard deviations? Both of them have the same spread, because all we're doing is we're just shifting the data by 7 units to one side. When we do that, the variation is not affected, right? The distances from the mean, they remain the same as before. So standard deviation for both Y and X, that is going to be the same. This is the general result that we get from this. If you have any two variables, Y and X, and they're related linearly like this, that Y is equal to X plus some constant or minus some constant, then the mean is also going to have that same relation. And the standard deviations for them, they're going to be equal to each other. Okay. Now, how is that used? Let's look at this example. You are given sigma t minus 35, that equals minus 15, and you're given sigma t minus 35 whole squared equals 82.23. Whenever you have expressions like this, sigma, and then inside brackets, you have some variable plus something or minus something, that's a linear transformation. What you would do in such problems would be, they're asking you, for example, in this case, to find the mean and the standard deviation of the times. Times are represented by t. So we want to find the mean of t and the standard deviation of t. The information that we're given is not for t, that's for t minus 35. What we do is we use a substitution in this case. We say, whatever is inside the brackets, just replace that with another letter. Substitute that with another letter. So this would become y equal to t minus 35, y equals t minus 35. And then you do your calculations in terms of y. So let y equals t minus 35. If y is equal to t minus 35, we know from that concept that we did that the means are going to have the same relation as well, and the standard deviations are also going to have the same relation. And the standard deviations are going to be equal, and the means are going to have that relation. And now what you do is you are given information in terms of y. You're given that sigma y is minus 15, sigma y squared is 82.23. You find the mean of y, that turns out to be this. You find the standard deviation of y, that turns out to be this. And now you know the relation between their means. Using that, you can find the value for t bar. And the standard deviations are equal. So standard deviation of y, if that's this, standard deviation of t is also going to be the same. Okay, so that's how we can use this. Let's look at another example of this. We have speeds given. They are represented by x kilometers per hour. They're represented by x for 70 cars, and we're given that sigma x minus 60, that is equal to 245. Sigma x minus 60, that is 245. We want to find the mean speed of the 70 cars. That means we're looking for x bar, right? Speed is x. We want to find the mean of x. How do you do that? Whatever is inside brackets, you replace that with another letter. So you can say it becomes y equals x minus 60. If that's the case, we know the relationship between their means is going to be this, and the standard deviations are going to be equal to each other. And now we do our calculations in terms of y. So we can say sigma y is 245. That's what we're given. Find the mean of y. That is 3.5. And now we know that y bar is equal to x bar minus 60. From that, you can find the value of x bar as well. Okay. Now they're saying his friend Sechin used values of x minus 50 to calculate the mean. Find sigma x minus 50. Again, you can replace this with another letter. I've used p here for that. We need to find sigma p, right? So that's another substitution that we can use now. P is equal to x minus 50. Now, if p is equal to x minus 50, what that means is the relationship between their means are also going to be the same. So what we can do is we know the value for x bar already from the first part. We can find p bar from that. P bar turns out to be 13.5. If p bar is this, use the formula for mean here. Sigma p over n, that should equal 13.5. And we find sigma p from that. That's what you were looking for. Sigma p was x minus 50. So sigma x minus 50 is 945, right? So using a substitution, it becomes fairly straightforward. Standard deviation of the speed is 10.6 kilometers per hour. Calculate sigma x minus 50 whole squared. Now, how do you think about this? Again, you can use a substitution. You can say p is equal to x minus 50. You have to find sigma p squared from this. Now, standard deviations are going to be equal, right? When you have linear transformations, standard deviations of all of these variables are going to be equal to each other. We are given that this is 10.6. So what we can do is we can say standard deviation of p, that is equal to sigma p squared divided by n minus p bar whole squared. Right? Just input values in this. If the standard deviation of the speeds is 10.6, standard deviation of p is also going to be the same. That's going to be the same. That does not change in linear transformation. So that means the standard deviation of x, that's the same thing as the standard deviation of p. Use the formula, you'll find the value of sigma p squared, and that's the result that you were looking for. Okay, so you can use substitution like this to do these linear transformation problems. Now, sometimes they ask you whether in a particular situation, mean is a good measure or median is a good measure. How do you figure that out? Generally, for most of the data sets, mean is the most appropriate measure because it uses all data points. It uses every single value in its calculation. However, there is one case in which mean is not going to be appropriate, and that is when you have extreme values in the data, when you have outliers in the data, in these cases, mean is not an appropriate measure. So for example, if you have a data like this, if you have two data sets like this, or is it the same data? Yeah, it's the same data. You've got a data set like this. It has an outlier. That's 450. Mean from this turns out to be 77.6. Median of this data, when you sort it, after sorting, the median turns out to be 16. Now, which is a better representation of the data? 16, because most of the data points are close to 16. Mean 77.6, that does not really represent this data in any way. Why is that not very helpful in this case? Because of this outlier. Because of this outlier, the mean is going to be inflated and it's not going to be reliable. So when they have when a data set has outlier, remember, mean is not going to be an appropriate measure. Okay, mean would not be appropriate when there's an outlier in the data. In that case, you would use median. Now, mean and median, they're both used for discrete data as well as continuous data. Mode is only used for discrete data. It's not used for continuous data, right? So if you can have any decimal value in the data, in that case, mode is not going to be an appropriate measure. It's only used for discrete data. Now, in mode, you'll sometimes get problems in which you have very small data sets. For example, just have these 8, 9 values like this, and you would be asked to find out whether the mode is not a very good measure in that case. Generally, mode is not a good measure when the data is very small, because a lot of times what happens is, by coincidence, one value might be repeated. For example, in this case, 2 is coming twice and the mode is turning out to be 2. Now, 2 is not really a good representation of this data, because 2 is actually the lowest value in the data. So that's not an average of the data in any way. It's coming twice in this data because it's small data, 5, 7, 8, 9 values. If something comes twice, that becomes the mode. It can be because of some coincidence as well. That's, some values repeated. It might not have any practical significance as such. So for small data sets, mode is not going to be very reliable, because in some cases, it can turn out to be the lowest value, the highest value that will not represent the average of the data. If you have a large data, for example, you've data about shoe sizes, and then you've got like 5,000 shoes. And in that large data, there's some value that's coming a lot of times. For example, 1,500 is the highest frequency in this data for size 9. That has some significance, because that's telling you that the size 9 is the most common size that is sold in a particular store, or maybe it's the most frequent stock size that they have. So that has some significance, because it's repeating 1,500 times. It's very unlikely that it's just by coincidence that some value is repeated so many times. But in small data sets, if something is repeated just twice, it can just happen by accident, by coincidence as well. So in this case, we say mode is not a good measure when the data is small, because it could be the smallest value or the largest value in the data sometimes as well. Okay. All right. Then we've got some diagrams. There are 4 diagrams that you have in your syllabus: stem and leaf, box and whisker, histogram, and cumulative frequency curve. Now, what about stem and leaf? First of all, you've got this data. Let's say you want to draw a stem and leaf diagram. Stem and leaf diagram looks like this. You've got 2 columns. One column represents the stem, the other represents the leaf. Now, how do you represent it? It's going to be sorted like this. You'll have numbers written in sorted order in stem like this, in ascending order like this, in stem. And in the leaf, you'll have the remaining digits. Now, how would that work for this data? These are the data points that you've got. You would first look for the smallest value in the data. That's 34 in this case. Largest value in the data, that's 91 in this case. So 34 to 91. These are the values that you have to represent on this diagram. In the leaf, you can only have a single digit. You can't have multiple digits in a leaf. So you know that this is the only thing that you would have in the leaf then. Okay, 4 and 1. So what about stem then? The 10th digit, they will go in the stem, 3 to 9. You would write down these values starting from 3, ending at 9, with no value being skipped. Even if, for example, you had no data in 60s, for instance, if this value did not exist, we would still write 6 here. We would not skip that. Okay, we have to write all values from 3 to 9 here, and then their corresponding leaves based on the data. This is 34, this is 35, you write 4 here, you write 5 here, and so on. Okay, for the rest of the data. You will do it like this. You'll start from the smallest values, mark the values in 30s, and then you sort them that, okay, 34 should come first and then 35, and then you cancel them out so that you know that you've used them. That will make things quicker. Then look for 40 values in 40s. There are 45, 44, and 41. And then you sort them first, write 1 first, and then 4, and then 5, and that's this part done, and then move on like that. Always do it with a pencil. Do not use a pen for this, because a lot of times what happens is when you're writing these things down, you realize later that you've ended up missing a value. Then crossing out in a diagram is not a good idea. Never do it with a pen. Always draw this with a pencil. It's a diagram. Okay, so do it with a pencil so that in case you need to erase something, you can do that. Now, there's some properties of the stem-and-leaf diagram that are important. You always have to write down a key for the stem-and-leaf diagram so that you can understand how to read this diagram. So in this case, if you write something like this, 5, 2, you can say this represents 52 in this case. Okay, this represents 52. If there's any unit that's appropriate here, you should also use that. You should also write that in the key here. In this case, there's no unit. It's just the number of tickets. So there's no unit, but you would write a key like this. So this represents 52, stem here and leaf here, and that's the key. Now, there's some properties that are very important for a stem and leaf diagram. The rows should be sorted. The rows should be sorted. Okay, everything should be sorted. In every row, the data points should be sorted. You have to represent the key. The vertical line between stem and leaf, that's very important. You always need to have that. Leaf can only have 1 digit. You can never have multiple digits in the leaf column. Okay, for one value, you would only have 1 digit for each value in the leaf column. In stem, you can have multiple digits. In leaf, you cannot. There should be equal spacing between the numbers that you've got. Now, this is extremely important because it's a diagram. You don't just write down numbers as it is. Its representation is important. The values should have equal distances between them, right? These gaps between the values, they should be standardized, okay? And they should be standardized in a way that all of these first values, they're vertically aligned. These are vertically aligned. These are vertically aligned. This is important. If you don't do this, you lose marks because of that. And there should be no commas or dashes that you use in the stem and leaf diagram. No commas, no dashes, no decimals. You don't have any of that in a stem and leaf diagram. You only have numbers with gaps between them. Okay, you only have numbers with gaps between them. Now, this is ungrouped data. Even in the form of a stem and leaf diagram, this is ungrouped data. So if they want you to find the median of the data, for instance, you use the method that you use for ungrouped data. What's that? N plus 1/2, right? For interquartile range as well, you use that method in which you find the median. Median divides your data into 2 parts, 1 part on the left side here and 1 part on the other side here. Of the median, find their medians. They will be lower quartile and upper quartile, right? So you have to use the ungrouped data methods on this for finding median and interquartile range. Now let's look at some examples of this. If you had data like this, 345, 366, 342, and so on. Now the leaf can only have 1 digit, right? So how do you figure this out? How do you figure out what to put in stem? Look at the smallest value in the data, that's 342. Largest value in the data, 363. So you have to draw this diagram for values between 342 and 363. How do you do that? In the leaf, you can only have the last digit. That means the first 2 digits, they will come in the stem. So 34, 35, 36, this is what you have in stem here. And then you can write down the corresponding leaf. And then you write down the key for that as well, that this represents 358, for instance. Okay, that's what the stem and leaf diagram would look like in that case. If you have decimals like this, for instance. What about this? Again, figure out the smallest value in the data, the largest value in the data. Decimals cannot be shown on the diagram. It's starting from 2.3, ending at 5.8. The leaf can only have 1 digit. So the rest is going to go to stem. So you write 2, 3, 4, 5 here. Do not skip any value. Even though we don't have any value that's 4 point something, we still have to write 4 in stem. And then You have 2.3, 2.7, 2.8, and so on. In the key now, you would represent how to read this. So 3.5, for instance, that means 3.5. Decimal will not be represented in the diagram. It will come in the key. Okay. Now you can have back-to-back stem and leaf diagrams sometimes as well. You have two sets of data in which one set of data is represented on the left side, the other on the right side. That's also possible. The data on both sides has to be sorted. So on the right side, it's sorted this way. Values close to the stem, they are smaller, and values away from the stem, they are bigger. On this side, the data is sorted in this direction, right? So it's ascending from right to left in the other case, on the left side. Sometimes you will have numbers written on the sides like this in brackets. In the questions that they would give you, they would represent the number of values in each row. So the first row has 2 values, the second has 4 values, and so on. And that's helpful generally when you're finding the median and interquartile range. Generally, we don't have to count them ourselves. You can just look at the number of values written on the sides. So that's what that would represent. Now, what about the key for this? It's going to be a single key. Don't write 2 separate keys for this. It's a single stem and leaf diagram. There has to be a single key for this. Stem in the middle, 1 value on the left side, 1 value on the right side. And the 3 numbers that you choose for the key, they should all be different. Otherwise, there will be ambiguity. You can't say something like this, 8, 2, 8. That's not acceptable because 8 is coming twice. There will be ambiguity whether you're talking about this 8 or this 8 when you write it on the side. All of these 3 numbers, they have to be different numbers. Okay. And then you can say this whole thing represents 85 kilograms. Unit is important for P and 83 kilograms for Q, and that's what your key is going to look like. Okay, so that's the stem and leaf diagram. These are the important points to remember. This is only used for ungrouped data. This is only used for ungrouped data. Some benefits of stem and leaf diagram. Sometimes they ask you for this. They ask you what are the benefits of stem and leaf diagram. Just a simple question, 1, 2 mark question like this. One benefit is that it shows all data. It shows all the data in the diagram, which other diagrams don't. So in case you wanted to go back to the original data, you can do that. From this, it shows you all the data that is there. Number 2, you can see how the data is distributed. So for example, just by looking at this diagram, if you've drawn this correctly with equal spacing, you can see that most of the data for P, for instance, is concentrated here in 90s. And for Q, most of the data is concentrated here. And then it becomes lower on the sides. And for P as well, it's lower on the other sides. So just by looking at the diagram now, if you just had numbers written, that would not make it clear where the data is concentrated. But in this diagram, you can see clearly that, okay, most of the data for P is in 90s. For Q, it is in 70s. So it tells you the distribution of the data, how the data is distributed. Okay, that's the other benefit of stem and leaf diagram. You need to memorize these. You sometimes just have to write these down as it is. Okay, let's move on. The next diagram is box and whisker plot. In box and whisker plot, you need 5 points. 5 points. And these 5 points are minimum, lower quartile, median, upper quartile, maximum. These are the 5 points that we have to draw for in a box and whisker plot. Okay. Now, this is an example. They've given you some values, lower quartile, upper quartile, minimum, maximum, etc. They gave you interquartile range in this question, and they also give you the upper quartile. First of all, you have to find the lower quartile. You can use this formula to find that. The values are in hours and minutes. So you first convert them to minutes, all of them, and then you just use this formula to find the lower quartile. Then they say, represent this information by using a box and whisker plot. Now, how do you do that? You will get a grid on the paper for this. For S1 is the only paper in which you get these graph grids for cumulative frequency curve, histogram, and box and whisker plot. You'll have the space and given in the question paper. Always use a pencil for this because otherwise, if you do it with a pen and get something wrong, you won't get an additional paper for this, right? And the additional page at the end as well, you don't have a graph paper. So don't make a mess of it. Do a pencil. You use a pencil for this. Do not use a pen. Okay, so how do you draw a box and whisker plot? Only one axis is important here. Horizontal axis, generally, you can draw, you can mark points on this horizontal axis. Then what you have to do is choose any line here. Choose any particular line here. It doesn't matter because the vertical axis does not represent anything here. So you can choose any line here and mark those points. You've got the minimum point, that's 30. And then the lower quartile, 54, median, 216, upper quartile, 282, and the maximum value. You can mark these points. And now the points on the sides, they will be joined with lines like this. From lower quartile to upper quartile, you would have a rectangle. Now, the width of this rectangle does not represent anything. You just have to make sure whatever is the number of values that number of boxes that you have gone on the upper side, in this case, 5 boxes, that should be the same number of boxes that you go on the lower side, 5 boxes. Okay, 5 up, then 5 down. Use the same number of boxes so that the graph remains kind of symmetric from the side, that this line is exactly in the middle of that rectangle. Okay, and then in the middle, and at the median, you draw another vertical line, and that completes your box and whisker plot. On the sides, it's your choice if you want to draw these vertical lines, small vertical lines like this. They're not necessary though. Only these lines are necessary. If you want, you can draw those vertical lines at the sides as well, and that completes your box and whisker plot. Okay. So that's what it looks like. Using this box and whisker plot, you can see again how the data is distributed, how much spread, how much variation is there in the data. If there's any skewness in the data, for example, in this case, median is on one side, the data is skewed. Okay, the data is skewed in this case towards one side. And this is how you draw it. Make sure that you label this for all the diagrams that you make. Always make sure that you label them appropriately. On the horizontal axis here, you would say that this is time in minutes. Use the units there as well. Sometimes you have to draw 2 box and whisker plots in the same diagrams. This is the same example that we saw above, in which we had the stem and leaf diagram given. But now, let's say we had to draw a box and whisker plot for this. Now, and firstly, they want us to find the median from this and the quartile weights. That means lower quartile and upper quartile from this. I told you how to do that. Find the median. The median will divide your data into 2 parts. Median is here. That divides your data into 2 parts. This blue part on one side, the green part on the other side. Find the medians of those parts. They will give you the lower quartile and upper quartile, and that will give you the interquartile range. Okay, so you can find that. Now, in the second part, they've given you the lower quartile, the median, and upper quartile for the other country as well. You can find the minimum maximum values from the data. This is the minimum value for P. The maximum value is 105. The minimum is 74. Similarly, you can find that for Q as well. And you would have these values, the 5 values, minimum, lower quartile, median, upper quartile, and maximum for both P and Q. And then you can draw those diagrams like this. Select any line on the vertical axis, at which you would mark the points for P. Select any other line for Q. It doesn't matter. So the gap between them does not matter because the vertical axis does not represent anything. So you just draw those points, mark those points here, and draw a diagram that looks something like this. Make sure when you do this, both the box and whisker plots, the rectangles that you have there, they have the same widths. Do not use different widths, since the vertical axis does not represent anything. You have to make sure that you're consistent. Whatever width you're using for one, it should be the same width that you use for the other. Okay. So if it's 3 boxes up and down for Q, it should be the same for P as well. And that gives you 2 box and whisker plots in the same diagram. And then they will sometimes ask you to make some comments on the weights, comments on the data. Now, when they ask you to make some comments, those comments are generally going to be on central tendency of the data and the dispersion of the data. In this case, this only measure of central tendency that you can find from a box and whisker plot is the median. And for dispersion, you can use either interquartile range or range. Both of them can be found from this. Now they're asking for 2 comments. When they ask for 2 comments, that means one comment has to be on central tendency, the other has to be on dispersion. On central tendency, we can say, look at the median. On average, we will say something like this. We have to contextualize our comment with the information that's given here. It's data about weights of 17-year-old males in 2 countries, right? So we have to refer to that on average, these are the averages. 17-year-old males in country P, they have more weights as compared to those in country Q, right? That's the kind of comment that you can make on central tendency. On average, weights of 17-year-old males in country P are higher as compared to those in country Q. What about dispersion? If you look at interquartile range, that's not very different. So there isn't really much that you can say from the interquartile range. That's your first preference. But if you can't differentiate based on interquartile range, the other possibility is range. You can clearly see the range of Q is much bigger as compared to P. So how would you write that? You would not just say that the range is bigger. That's not what you say. You would say the variation in the data, right? Range represents variation in the data. You would say the variation of weights for people in country Q is more as compared to the variation in weights for people in country P. Something like this, the variation in weights in country Q is more as compared to the weights in country P. Okay, so that's two comments that you can make on this. So for median, we say on average, we say something like this. We don't write median values. We have to, write this in words like this. And for variation, we say the variation in weights. We don't just say standard deviation is this, range is this. We have to use statements like this, general statements like this. Okay, then you've got histogram. This is something that you've done in O-levels before as well. How to draw histogram? Whatever data that you're given, first of all, you have to make sure that you eliminate the gaps between them. So in this case, we've got gaps 20 and 21. There's gap between them. You find their midpoints and find the true class boundaries, as we saw before as well. Find their true class boundaries. Find their true class boundaries. In this case, they turn out to be this. Okay, these are true class boundaries. And then in a histogram, on the vertical axis, you would always have frequency density. In A-levels, you would always have frequency density on the vertical axis. Okay, frequency density on the vertical axis, you have to label that appropriately. On the horizontal axis, you have whatever the variable is, that is marks, the number of marks in this case, that's what you have in the horizontal axis. Now, how do you calculate frequency density? Frequency density is frequency over class width. Now, for that, we need class width. What is class width? Class width is the upper boundary minus the lower boundary. Now, how do you find that? You are not just going to do 20 minus 1. That will be wrong. That's 19. That's wrong. The class boundary, the class width is going to be calculated after you have first found the true class boundaries. So you have to find true class boundaries first of all, and then use those true class boundaries to find the class widths. 20.5 minus 0.5, that's 20. 30.5 minus 20.5, that's 10, and so on for the rest of the data. And then frequency density is calculated as frequency over class width. You can use that to find frequency densities. And then you've got these frequency densities. And you've got these intervals, the true intervals, the actual intervals. These are the ones that you would draw there on the diagram now. You can draw them here like this. In this case, since the intervals are 0.5, 20.5, 30.5, it's often a good idea to start your axis in such a way that you have those values coming on these major lines. So start at 0.5 on the horizontal axis, so it becomes 10.5, 20.5, 30.5, and so on. It'll make it easier for you to draw that histogram. If you start from 0, then your bars will have to be passing through the midpoint of boxes. That's more difficult. You can do that as well if you want, but it makes it easier if you start at 0.5 like this. On horizontal axis, you can do something like this, and you start from a different number. But vertical axis, that always has to start from 0. Vertical axis cannot start from any other number. It always starts from 0. Vertical axis always starts from 0. So then you would just make bars like this. Make sure that there are no gaps between the bars. Sometimes they ask something like this as well, that they give you some chart and they ask you, what's the problem with this? For example, they will give you a histogram and it would have gaps between it. So you would say it cannot have gaps. That's one problem. Sometimes they will give you something in which on the vertical axis, it would be frequency. You would say on the vertical axis, there has to be frequency density. Right, so you'll find a couple of questions in the past papers where they ask you to identify what are the mistakes in this histogram, right? So there should be no gaps, and on the vertical axis, you need to have frequency density. That's what it would look like. Now, sometimes what happens is they give you a histogram again, and they want you to find some missing frequency. So they might have this histogram that's given, and some frequency here might be missing. For example, this might be missing. We don't know this, let's say. How do you find that? From the histogram, the areas of the rectangles, they represent frequencies, right? So for each rectangle that you have here, its area represents the frequency of that interval. Why? Because you can see that here, frequency density is calculated as frequency over class width, right? Frequency density is frequency over class width. So frequency would be frequency density into class width. So that's this base into height. Frequency density is the height. Class width is the base. When you multiply them, you get the area of the rectangle. That's frequency. So area of these rectangles, they give you frequencies. Okay, area of rectangles on a histogram, they give you frequencies. Then the last diagram is cumulative frequency curve. That's the last diagram that you've got. How do you draw this? You'll have a table like this. Okay, you've got this table, and you're given frequencies here. First of all, you have to convert this table to a cumulative frequency table. How do you do that? If 1 to 20, the frequency is 10, then less than or equal to 20, what's the total frequency? That's 10. Then less than or equal to 40, that's 10 plus 32, 42. Less than or equal to 50, that's 104, 62 plus 42, right? And so on. You find the cumulative frequencies from this, first of all. Once you have them, you have to plot these values now. The upper limit, the upper boundary, and the cumulative frequency curve. It's a very common error to end up plotting midpoints here on the graph. You don't plot midpoints here for cumulative frequency curve. You have to plot the upper boundary and the cumulative frequency. So 20 and 10 for the first point, and then similarly for 60 and 154 for this one. Upper boundary and the cumulative frequency. Plot all of those points and you would join them. Make sure on the vertical axis, you clearly show that it's cumulative frequency. On the horizontal axis, you write down whatever the variable is, that's number of rooms, and then you can just, plot those points, draw a curve through them. It should touch 0 here at the bottom. It should touch the x-axis, and your vertical axis has to start from 0 like this. That's what the cumulative frequency curve looks like. Now, one very small point. In this case, the variable is number of rooms. Number of rooms is a discrete variable, right? It cannot be in decimals. The number of rooms, it has to be an integer. So in this case, the interval that's given, that's 1 to 20, right? So we could just say in the cumulative frequency, it's going to be less than or equal to 20. But if it was some other variable, that could be continuous, for example, if it represented length of something. Now, length is a continuous variable. If for length, you were given this data, you would first have to adjust it. You have to find true class boundaries, because length can be in decimals as well. We have to basically figure out what to do with values between 20 and 21 in that case as well, because we can have decimal values as well. So in that case, the boundaries that you would use for this curve would be less than 20.5, less than 40.5, less than 50.5, 60.5, 70.5, and 90.5. In that case, these would be the numbers that you use if it was a continuous variable. In this case, it's a discrete variable. So that's why we're just using the values as it is, because they cannot be in decimals. Number of rooms cannot be in decimals. But if it was some variable that could take decimal values, in that case, you would have to adjust the intervals. And in the graph, then, these would be the values that we use. Okay? These would be the values that we use in the graph, then, in this case. Okay. So if it was length, for instance, which is a continuous distribution, then you would have to use these values instead of the actual values. Okay. Number of rooms is a discrete variable that can only be an integer. Length or any other variable that's continuous, you have to use the true class boundaries. So the true class boundaries would be 0.5 to 20.5 and then 40.5 and so on. So the upper boundaries will actually come from there. So that's a small detail that you need to be aware of. Let's have a look at this. Sometimes what happens is you get multiple cumulative frequency curves. Okay, I'll answer that at the end. So when you have multiple cumulative frequency curves, in fact, let's go back to that. Now, from this graph, you'll have to do some calculation. For example, they will ask you to find the median of this data. So you have 200 here. How do you find the median? You would divide 200 by 2. That's 100. Corresponding to 100, you would have the median. So whatever value you have on the x-axis here, that will be the median. Similarly, they can ask you to find the lower quartile, the upper quartile. How do you find them? Lower quartile is n over 4. Upper quartile is 3n over 4. You would find that those values on the vertical axis and find the corresponding values on the horizontal axis, right? Sometimes they can ask you to find percentiles like this. For example, 30th percentile. How do you do that? 200 into 30 over 100, that gives us 60. So corresponding to 60 on the vertical axis, you can see whatever value you have on the horizontal axis, and that will give you that value. Now, this is the more tricky part of this. Sometimes they say something like this: estimate the number of days on which more than 80% of the rooms were booked. So this data represents number of rooms and the frequency, the number of days at which each of these number of rooms were booked. So if you want to find out the number of days on which more than 80% of the rooms were booked, first of all, let's find the 80%. What's the total number of rooms that we've got? Total number of rooms, the maximum number of rooms that you see here is 90. Okay, what's 80% of 90? 80% of 90 is 72. So what that means is we are looking for the number of days on which more than 72 rooms were booked. Now on this axis, you can see this is 72. More than 72 means you're looking at the right side of this part. Okay, this part. Now, on the graph, that corresponds to this shaded part. So what's the number of days corresponding to that you get? That's from 186 to 200. This interval. So what's the number of days? 200 minus 186. It would not be 186 because 186 is the number of days for which less than 72 rooms are occupied. We want more than 72 rooms occupied. Okay, so we were here. We want more than 72 rooms occupied. What that means is that's from 186 to 200. That's 14 rooms. Okay, you've done these problems in O-levels as well. That's how you would do that. Sometimes what happens is they give you multiple graphs, multiple curves on the same diagram. And then they want you to do something based on that. So you've got these two curves. One is for one data, that's country A. Another is for the other data, that's country B. We've got information about 900 babies and we've got their birth weights. Okay, we've got their birth weights for 900 babies in each of these two countries. We've got their cumulative frequency curves. They're saying use suitable data from these graphs to comment on, to compare the central tendency and spread of the birth weights of the two sets of babies. Central tendency is mean, median, mode. On a cumulative frequency curve, the only measure of central tendency that you can find is median, right? So you can find the median and compare them. 50th percentile, the total number of values, the total number of babies was 900. Half that gives you 450. So corresponding to 450, you've got 3.85 for one, 4.5 for the other. So you can say, no, sorry, 3.85 for one and 2.05 for the other. You write down their medians and you compare them. Okay, 3.85 for B and 2.05 for A. We'll comment on that in a moment. So that's the median. That's one thing that you can comment on. And then for spread, you can use interquartile range from this data. 75th percentile, 25th percentile, find their difference, upper quartile minus lower quartile, and that gives you these interquartile ranges. And then you comment like this, you say, on average, the birth weights in country B are more than those in country A. That's one comment on central tendency. And the variation in birth weights is also more in country B as compared to country A. Okay. So that's what you can comment. You make these 2 comments based on these calculations. That's a 6-mark problem. So you have to do these calculations first of all, median interquartile range, and then based on that you make these 2 comments, one on central tendency and the other on dispersion. The only measure of central tendency that you can find from this data, from this graph, is median. So you use that. And for spread, you could either find range or interquartile range. If you can find interquartile range, that's a better measure. So that's what you would use. Compare them and you get the result. Okay, so that's all the concepts that you've got here. Let's have a look at just a few questions quickly and then we end. Okay, so we've got this data. These are amounts of money spent close to the nearest $10 by 27 people. Construct a stem and leaf diagram for this. Now, let's think about this. Remember, in the stem, in the leaf, you can only have 1 digit. In the leaf, you can only have 1 digit. Now, what's the smallest value in the data? That's 10. Largest value in the data? That's 570. Right? These are the smallest and the largest values. How do we think about what to put in stem and what to put in leaf? If you say the last digit only is going to come in leaf, then in the stem, that means you have data from 1 to 57. That's a lot. 1 to 57. You'll have to write down all of those values, 1, 2, 3, 4, 5, 6, all the way up to 57. And notice all of them are zeros here. So leaf is not going to be very interesting because it will just be zeros there. The last decimal is 0 for all of them. So what do we do then? These values are given corrected to the nearest $10. So that is why the last digits are all zeros. So using 1 to 57 as stem is not going to help in this case. We can think of it like this. This is 0, 1, 0, right? The 100 digit is 0 in this case. 0, 4, 0, 0, 6, 0, 0, 8, 0. So we're basically going from 10 to 570. 10 to 570. So in the stem, what we can do is we can use 0 to 5. In the leaf, we can have the tens digits. And since the last digit, the unit digit, is all zeros, we can just represent that in the key that we would write. Okay, so we make a stem and leaf diagram that looks like this here. We start from 0 and at 5. We write down these values in the leaf like this. For example, 10, 40, how do you write them? 1, 4, 6, 8. Similarly, for values in 300s, for instance, you've got, okay, let's look at values in 200s, for instance, these values. In the leaf, you have 0, 1, 5, 7, 8. Because in the leaf, you cannot have multiple digits. You can only have 1 digit. So you write 0, 1, 5, 7, 8 in the leaf like this. And then what you do is, in the key that you draw, and the key that you mention, you say something like this, 2, and then vertical line 3, that represents $230. So that 0, the last 0, that will come in the key here. That will be represented here. Okay, so that's the more complicated type of stem and leaf diagram that you would see sometimes, in which it becomes a bit confusing what to take as the leaf. Then you have to find median and interquartile range. We've talked about that before. In the third part, it says, an outlier is defined as any data value that is more than 1.5 times the interquartile range above the upper quartile, or more than 1.5 times the interquartile range below the lower quartile. Now, this is not a general definition that's only given in this particular question, right? And for this particular question, we can use that as the definition of an outlier. We have to list down the outliers. How do you do that? You've got this data. We are given the definition of an outlier in this question. More than 1.5 times the interquartile range above the upper quartile. What does that mean? Wherever the upper quartile is, you have to be 1.5 times the interquartile range above the upper quartile. And upper quartile plus 1.5 times the interquartile range. If any value is greater than this, that's an outlier. Similarly, let me just show that to you first. So upper quartile plus 1.5 times the interquartile range. If any value is greater than this, that's an outlier. So greater than 315, that's an outlier. And any value that's more than 1.5 times the interquartile range below the lower quartile. What does that mean? Lower quartile, subtract 1.5 times the interquartile range from that. Any value that's lower than that, that's also an outlier. So you can understand it like this. You've got median in the middle, right? You've got lower quartile here, upper quartile here. So if you go 1.5 times the interquartile range to the right of the upper quartile, this region is going to be an outlier. And then you go 1.5 times the interquartile range to the left of the interquartile, to the left of the lower quartile, this region is going to be outlier as well. So we understand from this, any value that is less than 35, any value that's less than 35 or greater than 315, that's an outlier. So we look at the data and spot any values that satisfy those conditions. 10 is less than 35, 570, 450. These are greater than 315. So these are the three outliers that we've got. Based on this definition, we said the outliers are $10, $450, and $570. Okay, that's how you interpret that. Okay, let's have a look at this. Now, just a few simple examples, and then we end. Find the mean weight of the 27 birds. We've got this data for some birds and their mean and standard deviations given for some turkeys and some geese. We want to find the mean of all 27 birds. We've got data given for them separately. How do you find mean? Mean is given by sigma x over n, right? Sum of all values divided by the total number of values. What's the sum of all values going to be? Mean of this data is 7.1, and there are 9 of them. What will be the sum of these values? 9 into 7.1. What will be the sum of these values? 18 into 5.2. So the sum of all values is going to be these two things added together, divided by the total number of values, that's 27, and that will give you the mean like this. Okay. Then they say weights of individual turkeys. They are denoted by xt, and for individual geese, we have xg. We want to find sigma x squared for both of them, and then find the standard deviation of all 27 birds. Now, what's the standard deviation formula? Standard deviation formula looks like this: sigma x squared over n minus x bar whole squared square root of that. That's the standard deviation formula. Now, for this, we need the value for n. We know that that's 27. Mean, we have found that in the first part. That mean was 5.83. So we've got those two pieces of information, but we do not know sigma x squared. Sum of all x squares. How do you find that? We've got information given for them individually like this. For turkeys separately and for geese separately, what we can do is we can use the standard deviation that we have for them. We can use the standard deviation that we have for them to find their sigma x squares individually, right? So we know for turkeys, the mean is 9. For geese, it's 18. That's given. No, there's something wrong here. Mean, that's the number of values, sorry. Number of values for turkeys is 9. Number of values for geese is 18. We've got their means given, 7.1 and 5.2. And we've got their standard deviations given. So we've got this information given in the form of the table above. If the standard deviation of turkeys is 1.45, we can use this formula to find sigma xt squared. Similarly, for geese, we can use that same formula to find sigma xg squared. So you find sigma x squared for turkeys, sigma x squared for geese. What's the overall sigma x squared going to be then? Just add them up together, and that will give you the overall standard deviation. This is the total sigma x squared divided by the total number of values. That's 27 minus mean squared and square root of that. And that gives the standard deviation of all of those geese. Right? So sometimes they give you problems like these in which they split the data into 2 parts. And you have to find the overall mean on the overall standard deviation. You can find the individual sums and then add them up together, individual sigma x squared, and then add them up together to use in the formulas. Okay. Okay, just a few more examples. Let's have a look at this now. We've done something very similar before as well, by say. This is linear transformation. Sigma x minus 45, that's equal to this. Sigma x minus 45 whole squared is equal to this. In these problems, I told you, you can use a substitution. You can say, let this equals y. So then sigma y is equal to 1 minus 148, sigma y squared equals this. Find the mean and standard deviation of the 36 values. Which 36 values? Values of x. So what we can do is we can find the mean and standard deviation of y, right? Find the mean and standard deviation of y. Mean of y turns out to be this. Standard deviation of y turns out to be this. Standard deviation of y turns out to be 80. Oh, there's something wrong somewhere. It's not supposed to be 80, I think. 3086 minus that, the square root of that, because both of them have to be equal to each other. 100 minus that. Okay, so this value is also 8.3. Okay, so what we do is we find the value of the mean of y, the value of the standard deviation of y, and then we say if y is equal to x minus 45, then the means are going to have the same relation. If we know y bar, we can find x bar from that. And the standard deviations are going to be equal. If the standard deviation of y is this, standard deviation of x is also going to be the same. Now it says one extra value of 29 is added. Find the standard deviation of all 37 values. How do we think about this now? We have another additional value that's 29 that is added to the data. Standard deviation of all those values. Now we need the mean for that as well. Now earlier we knew that the mean was 40.88, right? That was the earlier mean. Can we find the sum of all values from that? 1471.68 sigma x, we can find that. Now there's another value that's added, that's 29. It becomes, the new x bar becomes sigma x, the new sigma x, earlier sum, plus 29 divided by the total number of values, that's 37, and that gives the result for the mean. We do the same thing for standard deviation as well. We've got the old standard deviation. Earlier, the standard deviation was 8.30 that we found there. Use that to find sigma x square. That will be old sigma x square. Now, for the new standard deviation, you can say the sigma x square now is going to be this number plus the square of this number that was added. That's 29 squared. That's what you put in the numerator here, minus mean squared divided by n, and that will give you the result, which turns out to be 8.41. Okay. So you have these questions in which sometimes they add another value or remove a value. You need to be able to work with these problems as well. Okay, let's have a look at this. We've got this data that represents time after opening. That represents the number of people entering a store after a certain number of minutes that the store is open. For example, in the first 10 minutes, you've got 210 people, and so on. Afterwards, first of all, they say find the values of A and B. How can we do that? We know the total cumulative frequency, that's 540. So the sum of all these values has to be 540. So that gives us the value for B. And then this is missing, this value for A. What do we do for that? What information do we have? Okay, so what we can do is we can say this is 540, or we can do it this way as well. This is 422. Add 72 to that. That will give you this cumulative frequency. That's the value of A. That's pretty straightforward. The first part, you have to draw a cumulative frequency curve that looks like this. That's what the curve looks like. And then median time, again, that's also fairly straightforward. The total number of values was 540. 540 divided by 2, that's 270. You can find the corresponding value to 270, and that will be the median. So the first three parts are fairly straightforward. What about part 4? Calculate the mean and standard deviation. You've got this information that's also fairly straightforward. You've got midpoints. You can find xf, x square f, and find the mean and standard deviations from that. You've got these x values, and you've got xf, x square f. The only difference is that these values are given in the form of a column table here. Earlier, normally we have row columns, and this gives us in the form of a column. Earlier, and we have row tables. In this case, we have a column table. That's the only difference, but the process remains the same. This is the last part that I wanted to actually talk about. Use a graph to estimate the number of people entering the store between m minus half s and m plus half s minutes after opening. What does that mean? M is the mean, S is the standard deviation. Now we have found the values of M and S in the previous part. So they turn out to be this 18.2 and 14.2. M plus half S and M minus half S is input values there. You get 11.1 and 25.3. Now you want to find the number of people who enter the store between these time intervals, within this time interval, 11.1 to 25.3. Go to the graph. This is 11.3 and this is 25 point something. On the vertical axis, you get 230 and 385. So the difference between them, that will give you the number of values, which turns out to be 385 minus 230, which is 155. That's the result that we got. Okay, turns out it wasn't that difficult. Yeah, so let's have a look at this. You've got some data points here. This is ungrouped data. Don't think that it's a table, so it's grouped data. There's no frequency here. These are ungrouped values. This is raw data. So use the first formula, sigma x over n and sigma x squared over n minus x bar whole squared to find the mean and standard deviation. And you can do that. That's pretty straightforward. What about this? They say state with a reason which team has more consistent scores. What does that mean? More consistent scores? The one that has less variation in the data. That has less variation in the data. Now, look at the data and see which data has less variation. Now, they have not made you find the standard deviation for the other data. They've only made you find, okay, they actually gave you these values. So they gave you the values. You found the standard deviation for X as 83.14. And they're telling you that the standard deviation for B is 29.63. Now, they've also given you the mean value for this, although that's not going to be used anywhere. It's just for confusing you. Consistent means the one that has less variation. Consistent means, more consistent means less variation. So you compare the standard deviations, you say B is more consistent because the variation in these numbers is less. Okay, team B has more consistent scores because it has a lower standard deviation. Okay, the variation is less, so that means the consistency is higher. Okay, let's have a look at this. So the first part is straightforward. You have to find mean and standard deviation given this information. But then what happens is one person leaves the group and the mean age of the remaining 17 people is exactly 41 years. So in the first part, we found the mean, that's 41.39, standard deviation 13.16. We need to find the age of the person who left and the standard deviation of the ages of the remaining people. Now, how do you find that? They're saying that the new mean is now 41. New mean is now 41. Now, what was the sum of values earlier? 745. If one person is left, let's call the age of that person as A. Let's call that A. What's the sum of values now? 745 minus A, right? Divided by the number of values. It was 18 people earlier, now it's 17 people. Divided by 17, that should equal 41. And that should give you the value for A. Once you have that, you can find the standard deviation for that new data. That's not that complicated after that. So you can have some value removed from the data like this, and you might have to find the new means, new standard deviation, or some other missing information from the data like this. Okay, one last example. These were fairly straightforward examples, most of them actually. Summary of 20 values is given. Sigma x minus 30 is this, sigma x minus 30 whole squared is this. Again, this is coded data, linear transformation. A summary of another 25 values of x gives this and this. So you've got two sets of values. One has 20 values and the other has 25 values. We need to find the mean of all 45 values of x. How do you think about it? Use a substitution. You say y equals x minus 30. Then we can say sigma y is this, sigma y for the other one is 470. What's the mean for all of them? You add up both of them, divided by 45. That gives you the overall mean for y. And then you know that y bar is equal to x bar minus 30. Just use that to find the mean for x as well. Similarly, standard deviation for all values of x, do the same thing again. sigma y square is this for for 20 values. For the other 25 values, sigma y square is this. You find the sum of them to find the overall sigma y square. That's going to be the numerator here divided by 45 minus the mean squared and square root of that, and that gives you the result. And that's it. This is all that you need to know about representation of data. I hope that was helpful. It's been 2 very long sessions, but we're going to stop here now. If there's any problem, you can let me know.